Hi students, if you're watching this, I'm assuming you've already watched the video on isotopes and calculating average atomic mass based on their relative abundance. This particular video provides examples of when the problems are a little more challenging and they might not give you the relative abundance. Instead, they give you the average atomic mass of each isotope and they give you the individual isotopes masses and how you would calculate the relative abundance. But for a review, I'm just going to go through those last two slides from the last video, which atomic mass, we know that not all the atoms of the same element have the same mass because they are isotopes and they have a different number of neutrons. And they have different relative abundances, or they're found in different percentages in nature. So that way we must calculate what I like to call a weighted average. And that's what we see on the periodic table. So as a review, how do we calculate these weighted averages? We change their percents, their natural abundances, into a decimal form. So again, how do we do that? We can take any percent, 58.67%, and simply move the decimal over twice, 0.5867. Where a lot of students have difficulties and they make careless mistakes is if they see a relative abundance of 3.83%, okay, as a relative abundance, and they actually put the answer as 0.383. That is incorrect. If you were to divide 3.83 by the 100, remember you're moving the decimal over twice, your correct decimal for this percentage is 0.0383. So don't forget to move the decimal over twice and not make that careless mistake. But enough math review, let's get back to chem. So again, to get the average atomic mass, you take basically the relative abundance and you convert it into a ratio, decimal, and you're going to multiply it by the mass of that particular isotope. If there's 2, you would do it twice. If there was 3, you would do it 3 times. And if there was 4, you would just do it 4. Last time we provided the example where we used chlorine because chlorine had 2 isotopes. I wanted to make it pretty straightforward. We gave you the percentages of each isotope and the mass of each isotope. And then we converted the percentages to decimal form and we multiplied those decimals to their average or to the isotope's mass. So we did this and we showed for chlorine 37. We called it chlorine 37. It was roughly 37 AMU, 36.97. And we converted that percentage into a decimal by simply moving it over twice. And then we did the same thing for chlorine 35. Here's the mass right there. And then the percentage we moved over and we got the decimal of 0.757. We took the sum of those products, added them up, and we get our weighted average because they each contribute a little bit differently. We see that chlorine 35 is more abundant. It's, more abundant, so it has a larger contribution to that weighted average. And we see that's why on the periodic table that the average atomic mass for chlorine is not an integer, it's actually in a decimal form. To make it easy for everybody, you can just go to the hundredths place on your calculations. Don't worry about sig figs for that. I'm totally lenient with that. But how can this get a little more difficult? Because it can, especially now that we're in general chemistry as opposed to a preparatory chemistry course. So here I have an unknown element that consists of 2 isotopes. Isotope 1, they tell you the mass or the AMU of isotope 1. And isotope 2, it has a mass. They tell you that the average atomic mass for this element is 6.941 AMU. So there's a couple things. You can easily identify this element. How? You could look at the periodic table, right? And you could see for 6.941 AMU, that is lithium, okay? But that's not what this question's asking you. It's not telling you to identify the element. That would be too easy. It's asking you to calculate the relative abundance or the percent for each isotope. Now, how are you going to do that? You don't have, the percents. Well, remember, when you're converting percents to decimal, right? If I was to have, let's say 75%, right? That would be 0.75. So if I only had two isotopes and they add up to 100% because there's only two, then I would know that if one isotope is 75, the other isotope must be 25% or a 0.25. So how could I do it when I don't know the percentage of either isotope? Ah, that's where we use algebra. We can say, let, isotope number one's abundance equal X. And let isotope number two's relative abundance be. Now, how would I get from a 0.75, 0.25? What did I do? I just got 1 minus X. Now, a lot of students get confused because they think percents, it should be 100 minus X, but remember, we're converting it to decimal form, right? So 100%, like if I have 100% me, Sean, there's only one Sean. So that's what we're doing. We're making the abundances in decimal form, and it should add up to 1. So 1 minus X plus X adds up to 1, because 1, if I multiplied it by 100 to convert it to a percent, is 100%. So I'll let isotope number 2 abundance be 1 minus X. Now, why does this help me? Well, I can do what I did before. I can convert the abundance in terms of X and multiply it by its mass, and then set it equal, instead of I can add up those products and set it equal to the average atomic mass that they gave me. Before, I was trying to find the average atomic mass. Now they give it to me. So how do I do that? Okay, isotope number 1. I'm going to say the relative abundance. That's going to be the unknown. I don't know what it is. I'm going to make it X, and that's for the mass, and I'm going to multiply that by the mass of the first isotope. So the first isotope's mass is 6.0152. Isotope 2. Isotope 2. The average atomic mass is the mass for that particular isotope is 7.01601, which is right here. But I have to multiply that by, remember, the percent abundance, but I'm doing it in terms of X, so that's 1 minus X. And I put that right there. So then when I multiply these, because that's what I would do, when I multiply these, I would get X times 6.01512 AMU for the contribution of isotope 1 for its mass to the weighted average. For 2, though, because I'm going to distribute the 7.01601, I would get 7.01601 AMU minus, and then I would distribute it to the X, 7.01601 AMU. And then I would take these two products, and remember, I'm going to add it, and it should equal, when I take the sum of this, 6.941 AMU. That's how I determined the average atomic mass before. The difference was there were no X's because I knew the percentage. So when I do that, oops, let me see if I can erase that. I'm sorry, that's covering. There you go. So here is my weighted average. Here is my weighted average that was provided, and I set it equal to these, right, sums or these products. So X, and then the 7.01601 minus X. So what am I going to do? I'm going to combine like terms. So there's two terms with X's. I'm going to leave them on the right side. So I'm going to get rid of the constant. How do I do that? I'm going to subtract the 0.701601 AMU from both sides. That'll eliminate that. And I'm going to subtract it on this side as well. It'll give me a negative number, but that's okay, because what I'm also going to do on the right side is combine like terms. So I'm going to combine this term in terms of x and this term in terms of x, and I'll end up getting a negative x. So I end up getting on the left my constant in terms of negative. The reason why it's negative is because I subtracted a larger number from the positive. And then I get a negative x because in terms of x, this was larger than this term. It's a simple fix. How do I solve for x? Divide both sides by the negative 1.00089, and I get that x is 0.07494. So what did we say x was? X was the abundance of isotope number 1. So how do I get the abundance of isotope 2? Well, we said we were going to make it 1 minus x. So what do? 1 minus x, this is my x. When I subtract 1 by x, I get 0.92506. Now I take both of those in decimal form and I multiply by 100. And I get my relative abundances. So isotope number 1 is found 7.494% of the time, and isotope number 2 is found 92.506% of the time. And that makes sense. And I got a lot of chicken scratch up here, so I apologize. But if we look, right, if we look at this, isotope 2 is basically 7. And if I look at the average, it is much closer to 7 than isotope 1 having a mass of roughly 6. And that makes sense. Why? Isotope 2, which is roughly 7, is found 92.506% of the time. So the weighted average of 6.941 makes sense because it's closer to the more abundant isotope. And, oh, whoops, sorry. I see that right there on the periodic table. So that 3 represents the number of protons. Both of these isotopes are lithium because they have 3 protons. Why did they have different masses? They have different number of neutrons. Their relative abundances multiplied by their masses gave me a weighted average of 6.941, which was given in the problem. But what I had to do in this problem was figure out the relative abundance of each isotope. And that was trickier because what did I have to incorporate? A variable, and I had to use algebra. But you guys are solid. Your algebra skills are solid. I know they are. So hopefully this will help you. If you come across one of these in the homework, you will, because I have at least one of these. And you should know how to do this for chem. So if you guys have any questions, feel free to email me or post them on the Ask Question board. And I thank you for your time, and tune in for the next videos. Thanks.